Okay, so today we're going to be looking at section 8.1, special right triangles. And before we can explore the side relationships for special right triangles, we need to revisit the side relationship that exists for all right triangles, and that is the Pythagorean theorem. Pythagorean theorem says, in a right triangle, this is a very important part of it. You have to make sure that you are in a right triangle. If I have a right triangle, then this side relationship is correct, and you can use it. If it's not a right triangle, you cannot use this. It does not work that way. Okay, so we've used this many times. So the next thing we want to do is do a little exploration kind of thing. And so here we go. We're going to start with this right here. We want to find the length of the diagonal of each of these squares. So I have three squares here that we're going to look at. The first one here has a side length of 1. And because this right diagonal is the C side of a right triangle, I can use Pythagorean theorem. So 1 squared plus 1 squared is C squared. So this is 1 plus 1 is 2, so this is 2. And so C squared is 2. And so C then is equal to the square root of both sides, and plus or minus, but because it's the length, we know it's only plus. And so C is the square root of 2. Okay, let's look at the next one over here. Same process. I got 2 squared plus 2 squared equals C squared. Okay, that's a 4, that's a 4. So I have 8. So C squared is 8. We take the square root, so C is the square root of 8. But we can simplify this. Remember, the square root of 8 is a 4 times a 2. And so C is equal to the square root of 4 times the square root of 2. Okay, move on to the next one. We got 3 squared plus 3 squared is C squared. So C squared is equal to 9 plus 9, 18. And so C is the square root of 18, but that is 9 times 2. And so C then is equal to the square root of 9, which is 3 times the square root of 2. So when we look at this, we look for a pattern that we might see from this. And hopefully you see a pattern in here. Okay. And so what I see is that all of these answers have the square root of 2 in it. And the number in front is exactly the side length that we have. So even though you don't see a number here, it's the number 1 out front. So 1 times the square root of 2. The side length is 2 times the square root of 2. So what this tells me is the diagonal of a square of any size can be easily found for all lengths by following the Pythagorean theorem, n squared plus n squared equals c squared. And there I have 2 of those, so c squared is 2 n squares, and that's where the 2 comes from, because you have 2 of the same thing. When I square root both sides, I get the square root of 2 times n squared. The square root of n squared is n, that's where the side length comes in, and then left over with the square root of 2. And so that's where that comes from, right there. And so this gives us a pattern that we can now use for any squares and saves us from having to do Pythagorean theorem all the time if I know it's a square. Okay, so let's take a look and see what we just discovered here. And you can kind of see that I've already kind of done it over here. And so we can see that the pattern emerges that the length of the diagonal of a square is the side length times the square root of 2. Because all the sides and all the angles of a square are congruent and the diagonal bisects the angle, the isosceles right triangle formed by this diagonal is a special right triangle and is referred to as a 45, 45, 90 triangle, because the diagonal bisects this 90-degree angle, creating a 45-degree angle. It's isosceles because the base angles are equal and its legs are equal, are congruent. That makes this a right isosceles triangle. This is a special right triangle called a 45, 45, 90. And the side relationships are this right here. Side length, hypotenuse. So these go in order. So this tells me that whatever the side length is, the next side is the same thing, and the hypotenuse is that number times the square root of 2. This is what it refers to. Okay? So that is the 45, 45, 90 special right triangle. Let's look at another one. Down here, same idea. These, though, are equilateral triangles. So the characteristic of an equilateral triangle is that all three sides are identical in length and all three angles are identical in measurement. And since it's a triangle, each angle is 60 degrees. The altitude is from the apex, from a vertex to the midpoint on the opposite side. And basically what it does is it's in an equilateral triangle, it bisects this angle. The altitude bisects the side and it is perpendicular to the side. So what that means is that this distance from here to here, that distance from there to there, is half of the side length. So since this side is all ones, the distance from here to here is 1/2. It's half of that distance. So if this side length is 2, then this distance from here to here is half of that, which means this distance is 1. And from here to here, this distance is 3/2. And that's important to recognize as we go through this process. Because these is the altitude, we're going to call it h, just for the heck of it, for the height, also the altitude. And I can do Pythagorean theorem with these things. So by Pythagorean theorem, since I have a 90-degree triangle, I can do 1/2 squared plus h squared is 1 squared. And then since the h is one of the legs, we're going to subtract this to the other side. So I get h squared is equal to 1 minus 1/4, or 3/4. Take the square root of both sides, keeping the positive version only because it is a length. I get the square root of 3/4. And we want to simplify this, and so you square root the top and you square root the bottom. And the bottom is a perfect square as 2, and the top just stays the square root of 3. Okay, so far so good. Let's go over here and do this one. Same process. So I got 1 squared plus h squared is 2 squared. So h squared is equal to 3 because that's a 4 minus 1. And so h is the square root of 3. All right. Come over here. We got 3/2 squared plus h squared is 3 squared. So this is h squared equals, this is 9. Okay. So this would be a 9 minus 9/4. Okay. And so as we work this out, we have 9 minus 9/4, and you're going to get 27/4. So when I square root both sides, I'll get the square root of 27/4. 27 is 9 times 3. So I get the square root of 9 times 3, the square root of 4. And so as we clean all this up, we'll get a 3 times the square root of 3/2. And so we look at this pattern, and do we notice anything? A little bit harder to see this one because of the fractions that were involved, but they all have something in common. They all have a square root of 3. So if I take that square root of 3 and break it apart from the number itself, this becomes 1/2 times the square root of 3. This right here is just the square root of 3, so it'd be like a 1 times the square root of 3. And this over here is 3/2 times the square root of 3. And you'll notice that this number right here, this number is that length we found right here, that half length. So if I take this half length and times it by the square root of 3, then I get the altitude. And that makes it a little bit easier to do. In generic terms, okay, if I have the equilateral triangle altitude and the side lengths are ends, then this distance from here to here would be n divided by 2. Okay, and I don't want to deal with fractions anymore. So what we're going to do is we're going to change these values just a bit because I don't want the fraction down there. So instead of calling those n's for simplicity's sake, let's make them 2 times n's. So all the lengths are 2 times n. which makes this down here a simple n. That's a little bit nicer to deal with. So if I know the short side over here, then I can use Pythagorean theorem as n squared plus h squared is 2n squared. So h squared is 4n squared minus n squared, which is 3n squared. So see where it comes from? And so h is the square root of that. And so then I get n times the square root of 3. So what does all this mean? Okay. This gives us the next special right triangle, and I'm just going to show it to you because I ran out of room. And so this is the second one. It's called a 30, 60, 90 because the diagonal, remember the altitude, this is the altitude right here. The altitude bisected the angle, so a 60-degree angle became a 30-degree angle. And I used the same number notation I just showed you. This is another special right triangle, the 30, 60, 90. Here's the ratios. So if I know that short side, so the key here is knowing the short side. If I know the short side, then I can find the other two. The short side times the square root of 3 is the middle side, and 2 times the short side is the hypotenuse. So those are the two patterns that we want to deal with, and then we can do some problems associated with that once we know them. So let's do some examples. Okay, let's find the missing side length. So I have two side lengths here. I have an XZ, and I have a YZ. I have a 45, 45, 90. This is the hypotenuse because it's opposite the 90-degree angle. So because of that, I know it's an isosceles right triangle, which means this side is exactly the same as that side. And because of the ratio that we know, leg, leg, and the hypotenuse, this is simply the leg side times the square root of 2. That's the pattern. Okay. If I go over here, notice I gave you the hypotenuse in this example. Well, whatever this side is, to get to the hypotenuse, I multiply it. So this here is times the square root of 2. So if I want to go back, I just simply divide by the square root of 2. So this tells me, and then these two things are exactly the same. So KJ is the same as KL, which is the hypotenuse length divided by the square root of 2. And you can see the square root of 2's are going to cancel out, and you become simply 12. So these are 12. Okay. Over here, we have a 30, 60, 90. This is the short side. Always identify the short side, because once I know the short side, then I can find the hypotenuse, which is simply the short side times 2. 2 times 6, which is 12. And the long side, PQ, is the short side times the square root of 3. The short side times the square root of 3. So 6 times the square root of 3. And that's it. Same thing here. I gave you the long side. I know this is the long side because it's opposite the 60-degree angle. And so to go from the long side to the short side, always go to the short side. You're going to divide by the square root of 3. So that means UV is 9 times the square root of 3 divided by the square root of 3, or simply 9. And then TV, which is the hypotenuse, is the short side times 2, or 18. Okay? So remember, for 45, 45, 90, you had n times the square root of 2. For the 30, 60, 90s, you had n times the square root of 3, and then 2n. Okay, so remember those ratios. That's how we solve these. So now I have these two down here. This is a 30, 60, 90. This is the long side. So always go from whatever side they give you, go to the short side. Okay, in a 30, 60, 90, find the short side. Whatever they give you, go there first. So to go from this back to the short side, I have to divide by the square root of 3. So that means BC is 28 divided by the square root of 3. Okay? So that's where we start with BC. We need to simplify this. This is a radical on the denominator. We don't like radicals in the denominator. So you're going to do what's called rationalizing the denominator. To remove a square root of a number, you simply multiply by that number and you squared it. So it offsets the square root. But I can't just do it to the bottom. I also have to do it to the top. See, this is the equivalent of timesing by 1. So we're changing its look, but we're not changing its value. So this is 28 times the square root of 3, and then the bottom just becomes a 3. You look to see if anything can reduce. Never go into radical to reduce. Nothing there will reduce. This is your final answer. That is BC. And BC is the short side. So AB is the hypotenuse, and AB is 2 times the short side. It's 2 times whatever BC is. So it's 2 times the 28 square root of 3 over 3. So as I multiply this together, nothing can reduce or anything like that. So it's just going to be 2 times the 28 or 56. And so that is AB. Likewise over here, same process. This is just for the 45, 45, 90 triangle. I need to go from the hypotenuse to the leg. So to do that, I have to divide by the square root of 2. So whatever we do here, I know that AC is going to be equal to BC, and it is 14 divided by the square root of 2. Okay? And so here, we need to rationalize this one. So square root of 2 to the top and bottom. This gives me 14 times the square root of 2 divided by 2. And you'll notice that this time, not the radical, but the 14 divided by 2 can reduce. And so then we can reduce this down. And AC, which is BC, is going to be 7 times the square root of 2. And there's my answer for those. Okay? And so we'll do more of these together in class, but that ends this video.